Hey guys, what's the crack? So in this video, we're going to go over the ideal gas laws. And then once we go over the ideal gas laws, and look at these equations, we're then going to try to answer this equation. And hopefully you can see that they do say molar mass. So you might think moles doesn't come up in physics. Moles is on my physics data sheet or my formula sheet. But yes, you're assumed to know it because you were supposed to memorize it in your GCSE chemistry exam. So it's assumed that you remember it for your physics exam. Okay? So ideal gas laws. Ideal gases, they follow these two equations all the time. Okay, so what do these two equations even say? Two equations says P is for pressure, V is for volume. Capital N is the one that causes a little bit of bother. Capital N stands for the number of particles or the number of molecules. So you can say number of particles or you can say number of molecules. Okay, K is our Boltzmann constant, and that is got, obviously it's a constant, so it's got a set value of 1.38 times 10 to the negative 23. And T is your temperature, and remember temperature here has to be in Kelvin for that equation to work. Okay, so what Kelvin is, and why we use Kelvin is because 0 Kelvin is always known as absolute zero, right? It's the coldest something can be. And because it's really cold, that's why it's really negative temperature, it's negative 273 degrees Celsius. Technically it's 273, like 0.15, but in your exams, they don't care about that as long as you remember the 273. So if I wanted to go into Kelvin all the time, what we do here is you just have to add 273. Okay, the next equation says PV, so again, pressure times volume. The little n stands for number of moles. So little n again stands for number of moles. R is called your molar gas constant. Again, that's a constant given to you. That number is 8.31. Again, T is your temperature, always measured in Kelvin for that equation to work. So number of moles. What is a mole? Okay. So what they did is, you'll probably remember from your GCSE chemistry, is remember we use carbon 12 as our relative, right? The one we compare it to. So what they said is that 1 mole of carbon 12 has got a mass of 12 grams. Okay, so that's our relative. So what we're saying is 1 mole is given like a certain number of particles, right? The same way that if we have joules, an easy way to write joules is electron volts, right? Because normally it's really negative numbers. So electron volts is just an easy way to imagine joules when you think about energy of electrons. Same way with a mole is just representative of a number of particles. And the number of particles it represents is Avogadro's constant, which is 6.23 times 10. Oh, that's my test there. What is Avogadro's constant? 6.23, I want to say times 10 to the negative 23, but let's just double check it because we got a data sheet anyway. So on our data sheet, it says that your Avogadro's constant is 6.02 times 10 to the power of 23. So what that's telling us, that's the number of particles inside 1 mole, okay, 6.02 times 10 to the power of 23. So you don't really need to know that. It's just like a reference point for you. So what we're saying is basically that the equations you need to remember from your GCSEs is number of moles equals mass divided by the relative molecular mass. Some people write that as MR to represent relative molecular mass. Doesn't matter what way you write the equation, as long as you know number of moles is mass divided by relative molecular mass. But because this was a chemistry equation, you have to remember that the mass there is in grams, right? So mass there is in grams for this equation to work. Relative molecular mass, what that is, that's just the mass number. So if it was carbon 12, the mass number there would just be 12. If it was uranium 235, the mass number, the relative molecular mass number is the 235. If it was like lithium 73, the mass number is that 7 because we know that's the mass number, right? The total number of protons and neutrons inside that nucleus. So our relative molecular mass number is just always that top number on your elements or on your atoms. The other equation you need to know is that the number of particles there are is equal to the number of moles times by Avogadro's constant. Okay? So again, Avogadro's constant tells us the number of particles in 1 mole. So to find out how many particles we have in total, just take that number and multiply by the number of moles that we have. Okay? So again, these are equations that you need to memorize, especially in AQA. Okay? Okay, so coming back to what even is an ideal gas. So ideal gases, we know that we can assume ideal gases, we can model ideal gases if they obey certain rules. And you need to know what those certain rules are. The rules are, we can use ideal gases because what we can assume is that the volume of a particle or of a molecule is negligible, or basically tiny. So the volume of a particle is negligible compared to the volume of the gas. Okay, that's an easy one to remember because the other point, normally it's a 2 mark to say what laws or what rules do ideal gases obey. This rule is easy to remember because for the second rule, you basically just repeat it, but you change volume to time. So what we're saying is the time of a collision, so when two particles collide, time of a collision, is negligible compared to the time between collisions. So what we're saying is if we've got all these, let's say I've got a balloon with all these gas particles inside them, the time it takes for two gas particles to collide basically is so small we can just ignore it compared to the time it takes between collisions for that gas particle to hit the edge of the balloon and come back again. Okay, other things we assume is that all collisions are elastic. So what that means is basically the kinetic energy is conserved, and we're assuming that there isn't any potential energy, right? There's no forces between these particles. So we're assuming there is no potential energy and all the collisions are elastic. Other things you could say is that you could say that the gas particles all move randomly, but again, the best ones I think to learn are these two because you'll always get the marks. Sometimes the mark schemes are tricky and they don't like it or they don't give you marks for saying all collisions are elastic, and sometimes they do, but they always give you the marks for these two. So I'd highly recommend you learn these two because again, it's just the same vocab, you've just switched the word volume for time. Okay, gas laws, there's 3 of them also we need to know about. The free gas laws are Boyle's law, Charles' law, and the pressure law. Okay, so how do you remember the difference between them? It's up to you how you remember it, but the only way that I can remember it is I think about the word boil, okay? The word boil to me makes me think of boiling, and if I boil water, I think about increasing the temperature, right? So if I boil water, I'm thinking that I'm increasing the temperature, so increasing the temperature, but the word is spelt wrong, so it's actually nothing to do with boiling, so it's nothing to do with temperature. So Boyle's law really is pressure and volume, okay? The pressure law then has to have pressure in it, because we call the pressure law. It can't relate pressure and volume, because we just use volume here, so the pressure law must be relating pressure and temperature. Then Charles' law uses the other 2 terms. Charles' law is not going to use pressure again because we've done that twice. This one's going to be volume and temperature. So we're going to see how they're related. So Boyle's law tells us what's going to happen if we compare pressure and volume. So we say, let's say we drop the volume. So if we make the volume really, really small, the pressure is going to increase. So those 2 are inversely proportional. So pressure and volume are inversely proportional. If you think about Charles' law, volume and temperature, let's say we make the temperature really high. So the temperature gets really high and we want the pressure to stay the same. That means the volume must also increase. So these ones are directly proportional. Okay, think about pressure. Again, if we increase the temperature, but we keep the volume the same, the pressure is going to also increase. So that's why these ones are also directly proportional. And that's why you can combine these equations then to get that equation P1V1 over T1 is equal to P2V2 over T2. So what we're saying is volume and temperature are directly proportional. So another way of writing directly proportional is to say that volume equals some constant times the temperature. So volume divided by temperature always equals a constant. So that's why you see volume over temperature here. Here pressure is inversely proportional to volume. So what we're saying is pressure equals some constant divided by volume. So pressure times by volume equals some constant. And again, pressure and temperature are directly proportional. So we can say that pressure equals some constant times the temperature, or that the pressure divided by the temperature is equal to some constant. Okay, so those are our free gas laws. So now if we look at the question, so the question says that we want to calculate the number of moles and the mass of air in a balloon. We've got the temperature, but it's in degrees Celsius. So hopefully the first thing you're doing is convert it into Kelvin. Remember, we just add 273. My mental math is shocking. So we do 273 plus 17, and you get a temperature there of 290 Kelvin. So I know the temperature. I know the pressure is in kilopascals. So just make a little note for yourself. Remember, that's times 10 to the power of 3. We've got the volume in meters cubed, and I've got molar mass. So again, I'm trying to think of the number of moles and mass. So what I would do is I look at my 2 equations, see which one's got moles in it, and clearly this one here has moles in it. So that's probably the easiest one to use. So what I'm going to write down is pressure times volume equals nRT. So So what I'm going to do first is I've got the pressure. I got 160 times 10 to the power of 3 times by my volume, which is this number, 0.00084, is going to equal to the number of moles times the molar gas constant, which is 8.31, times by my temperature, which is 290. So what we can do now is just solve through for what number of moles is. So to find the number of moles, all we're going to do is 160 times 10 to the power of 3. We're going to multiply by our volume, which is 0.00084. And then we're going to divide by our molar gas constant, which is 8.31, times our temperature, which was 290. To get our number of moles there is going to come out at 0.0, mine says 5576 or 558 moles. So moles, M-O-L, so that's an SI base unit. Okay, so I found the number of moles, that bit's done. Next it says I want to find what the mass is. So what they told me here is the molar mass of air. So if I look at these units, what it's saying is 0.029 kilograms is for 1 mole, okay? So what I'm saying is if I have 1 mole, I know the mass of 1 mole is going to be 0.029 kilograms, right? That's what it means. Remember, if it's like 10 meters per second, it means it goes 10 meters every second. If it is 0.029 kilograms per mole, it means that 0.029 kilograms is the mass of 1 mole. So if I don't have 1 mole though, I have this number of moles. I want to figure out if I have 0.0558 moles, what is that mass going to be? So you can see what do we do to this number is the same as we're going to do to this number. So here we multiplied by 0.0558. So this time I'm going to do the same to that side, multiply by 0.0558. So we'll do 0.029 multiplied by 0.0558. And we're going to end up with a mass of 1.62 times 10 to negative 3 kilograms.